Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll investigate how thread affinity can enhance OpenMP performance on the Betzy Linux cluster. Thread affinity governs the assignment of threads to hardware resources like CPU cores, boosting performance by leveraging hardware architecture. By controlling thread placement, we can optimize cache usage and memory access, thereby enhancing the efficiency of parallel programs. We'll carry out affinity testing for matrix multiplication using the same matrix dimension of 16,384 as in our previous videos. It's essential to set the value of n to 16,384 in our Python testing script for precise performance calculations. I've updated the Python testing script to include OpenMP affinity. We'll start testing with OpenMP places set to cores and OpenMP processor binding set to spread. We need to specify the OpenMP affinity setting in the execution command, along with the desired number of threads to use. We simplify our workflow by using the Intel alias to access the latest Intel Fortran compiler and matplot for the newest versions of matplotlib and NumPy modules. We switch from the login node to a regular compute node using our setup Python script. Here, we'll ask for one node equipped with 128 cores to perform our OpenMP affinity tests. We'll also instruct our interactive job to wait in the development queue. After a short wait, we're directed to the B3248 node to conduct our multi-threading affinity testing. We'll commence our testing phase by executing our Python script tailored for testing purposes. The Python script initially displays the compilation command before proceeding further. It's crucial to compile and execute on the same compute nodes. Compiling on login nodes and executing on compute nodes can lead to unwanted effects due to potential differences in architecture. We'll evaluate the performance of the executable program by adjusting the thread counts and employing spread affinity binding. We'll compare the results obtained with spread affinity binding, highlighted in red, to those without any affinity applied, highlighted in blue. In this test, transitioning from 1 to 2 threads, we achieve a speedup of approximately 1.93 with OpenMP affinity. Without affinity, the speedup was about 1.94. When transitioning from 2 to 4 threads, we observe a speedup of around 1.92 with OpenMP affinity. In comparison, without affinity, the speedup was about 1.91. The results for the other thread numbers are not presented here, but they will be incorporated into the figure generated with matplotlib. The testing script is applying matplotlib to create a plot illustrating how wall time, CPU time, and thread count relate in our matrix multiplication program. First, we'll display the wall time values in the figure. Next, we'll present the CPU time values. In summary, we'll incorporate the speedup values with the wall time and CPU time data. It's evident that multi-threading with affinity shows robust performance up to 32 threads, highlighting the significance of optimizing multi-threading with affinity for efficient parallel execution. In our upcoming affinity testing, we'll continue using the cause setting for OpenMP places, but adjust the OpenMP processor binding setting to close. We switch to the standard compute nodes using our Python setup script, asking for a single node equipped with 128 cores to conduct our OpenMP affinity tests. We then queue our interactive job in the development queue. After a brief interval, we're redirected to the B1232 node to proceed with our OpenMP affinity testing. We'll start our testing phase with the Python script. The Python script first shows the compilation command and then executes it. We'll use the executable program to test it with different thread counts and affinity settings using close binding. We'll compare the results using close binding, highlighted in red, with those using spread binding, highlighted in blue. We observe a speedup when transitioning from 1 to 2 threads, reaching approximately 1.97 with OpenMP affinity using close binding. By comparison, the speedup with spread binding was about 1.93. Transitioning from 2 to 4 threads, we observe a speedup of around 1.92 with close binding affinity. Utilizing spread binding achieved the same speedup. The testing script utilizes matplotlib to generate a plot depicting the relationship between thread count and both wall time and CPU time in our matrix multiplication program. Initially, we'll present the wall time values in the figure. Following that, we'll show the CPU time values. We'll conclude the figure by adding the speedup values alongside the wall time and CPU time data. It's evident that multi-threading with affinity has good performance up to 64 threads, highlighting the importance of optimizing multi-threading with affinity for efficient parallel execution. Close binding demonstrates better performance compared to spread binding on the Betzy Linux cluster when using 64 or 128 threads. On the other hand, spread binding has better performance when using 16 or 32 threads. In our next video, we'll provide a summary of our OpenMP experiments on both the Fram and Betzy Linux clusters. I am looking forward to the next video. Wishing you all happy computing in the meantime.